Welcome everyone. Today we'll be looking at the notes worksheet entitled Inverse Functions Day 2. And obviously this is a continuation of yesterday's lesson. We kind of built up the idea of an inverse conceptually, did a couple problems, there were some conclusions to be drawn, and hopefully you had some pretty good success with that. So this is obviously just an extension of that. We'll formalize things up a little bit as we get into some harder functions and looking at their inverses, but basically the premise will be the same. So let's kind of start it out here at the top. I see something along the lines of verifying inverse functions with compositions. And I think I had mentioned this in one of the notes worksheets with compositions, that there was a relationship between inverses and taking the composition. So here's what we'll take a look at, and we'll kind of illustrate this with a little flowchart momentarily. But if you get a chance, kind of box that up here. So what happens is when you have a function and its inverse, and you apply a composition with it, basically what you start with, and that would be the input right here, is what you end with after the composition. And it works in either direction here. So this would read the inverse of f composed of the inverse of f of x, and that equals x. And then the reverse is also true as I come over here. Again, what I start with is what I end with. And so in this particular case, I would read this as the function composed of the inverse of f of x is equal to x. And so let's kind of take a look at that. And again, it really just illustrates it conceptually. And then it allows us to do some checks as well with some of our work here today. So it does say on your paper, use a flowchart to illustrate this relationship. And I guess here's how we'll start it out. Obviously, we start with an input. So put a little X on your paper just like that. And I'm going to go ahead and kind of start with the generic input right there. And remember, and as a matter of fact, I think I'll do this one just FYI. So draw that arrow coming on through here. And basically what would happen with that composition is that input goes into the function machine. We'll call it f. And remember, f just manipulates that input. And after it manipulates it, out comes the output. So we get f of x. And that looks great. So remember how a composition works. Something goes in, something comes out, except we're not done with the process. That output right there becomes the input of a second function. So composition, of course, good little refresher on this. Now here's how this would play out, of course. If you look at the notation, and it pretty much speaks for itself, f of x becomes the input of the inverse. And so in this particular case, what I'm going to do is draw an arrow and do one more function machine. And remember, you set up the rules of the inverse based on what we talked about yesterday. And essentially, here's your inverse of f of x right there. And basically, conceptually speaking, these rules right here very simply just undo these rules right over here. So I started with this and apply these rules. Then I go right back in and undo those rules in essence. So here's how I'm going to write it on your paper. Just those rules. It just undoes f. Each and every one of those. Again, remember that analogy I used yesterday. This would be like wrapping a gift. This would be unwrapping the gift. And of course, if I wrap a gift and then unwrap a gift, I'm pretty much left with what I end with. So let's go ahead and do it completely. This would be the inverse composed of f of x. And again, because they undo each other, I'm just left with what I start with. So it again, it offers a way for us to do some checks as we go through the process right here. All right, so let's take a look at it conceptually with example 1. Just kind of talk about that process one more time. And then again, I think we'll formalize things up a little bit, have some strategies down below there, and we'll take a look at some things. So example 1 on your paper, it says let f of x equals 2x minus 4. And I guess in terms of the function, let's kind of talk about this piece. I think everybody would probably say whatever input I give you, you would multiply it by 2 and then subtract 4. Okay, so just like yesterday, in this case I would do those two operations for any input to get the output. So I think you would probably all agree that in order to unwrap that gift, I would add the 4. Remember, start with the bow. So add the 4 and then divide by 2. And so it looks like if we do those two things, and I'm going to go ahead and just start my process of writing that inverse over here. I'm going to add the 4 and then take all of that and divide by 2. And that, of course, should be the inverse of f of x. Now what we want is basically a way for us to confirm that, to actually see if that truly is. And how would we do that? Well, again, we graphed yesterday and we saw some characteristics and some conclusions with this. But algebraically, there's a way to verify this using, and again, there's the idea, compositions. So I'm going to certainly do it one way. Maybe you can do it that way and then the other way as well. We'll just kind of see how this goes for part B. But basically what I would do is the two different approaches here. So I'm going to do this one at the top, everybody. I'm going to do the inverse composed of f of x and see what we end up getting. So the inverse composed of f of x, and that would be taking f of x, which is this, right here, and that replaces the input of the inverse. So I think everybody would hopefully see it as 2x minus 4 plus the 4 and divide by 2. And I think you can kind of see how this is going to play out here. If it's okay with you, I'm going to skip half a step. But the minus 4 and the plus 4 cancel out, and then I get 2x over 2, which is just, of course, x. And again, what I start with, these undo each other, is exactly what I end with. Now, I'll take a moment, and if you can do the same, maybe you can be a little quicker than I am. But let's try this piece right here. And it should work in both directions, again, because they're essentially undoing one another. So let's try this. I'm going to take the function and compose it of its inverse. So here's the inverse over here, everybody. That becomes the input of the f function right over here. So instead of 2 times x, it's 2 times x plus 4 divided by 2. And then a minus 4 on the back. And again, if you don't mind me skipping half a step here, we can hopefully see this unfold. I can distribute, well, not distribute, but cross-cancel these 2's right here. So 2 on top, 2 on bottom would cancel. And then I do get just x plus 4 minus 4. And that should cancel, obviously, to just getting x. And so you can see, obviously, we did our inverse correctly there because we verified, we confirmed it with compositions. And I hope that illustration makes sense as we go through the process here from this to this to this, and it's exactly what you end up with. Okay. Now, just as a side note, now we're going to formalize things up momentarily. One of the things we're going to see, one of the applications we're going to see with inverses comes up in just a little bit. The two very big families of functions that we're going to explore, which is going to take us some time, they happen to have this exact relationship. They're going to be inverses of one another. And so you'll start to see something called exponential functions emerge and something called logarithmic functions emerge. And understanding that inverse relationship is, excuse me, kind of key to being successful with that unit. All right. Well, let's summarize a few things from yesterday. We'll throw some notation in, and then talk about some strategies here down below. So here's what I have on your paper. It should say something like finding inverse functions. And, you know, basically what we kind of talked about yesterday, what we found is that all of the x's and y's on the function switch in order to get the creation of the inverse. So the way I'm going to write it up here is to basically interchange the roles of x and y in the function. When you do that, you have basically created the inverse. That's going to be the easy part. The only dilemma with that is interchanging the roles of x and y is not going to put it in its most opportune form. And so what we're going to have to do is just work with it. And we're going to change the form without changing really too many values in there. So let's see what I have on your paper. It should say something like, if a function is defined by y equals f of x, and so let's go ahead and play that right here. And again, this is just really a notation piece. So if a function is defined by y equals f of x, then the inverse is defined by switching the roles of x and y. So this would basically be your inverse. So x equals f of y. Now again, if you've been paying attention all year long, we've never really worked with equations x in terms of y. It's always been our dependent variable in terms of our independent variable. So what we want to do in this particular case is switch x and y, That's exactly the premise that we're under. But then to actually solve for y, get it in the form that we're working in. And that is what is called explicit form. And you'll see this a lot over the next couple of years, talking about the explicit form of an equation, and that explicit form will be y in terms of x. And so you can kind of see right here, and I'm just going to throw some notation your way. If it bothers you at all, just ask about it. But basically, the premise would be here, I want to solve for y. So I want to undo taking the function of that y, the function value at y. Well, how do I do the function value at y? In essence, it actually goes back to the top of the page. What I'm going to apply here, everybody, is the composition. And watch this. Again, don't get too caught up in this piece. It's really the strategies down below that we're going to sort of see in action. But basically, if I apply a composition and take f of y and make that the input of the inverse, I should see those two pieces go away and should get a y equals. Well, we do know, of course, that when all is said and done, anything I do to one side of an equation, even if I'm doing it just notationally here, anything I do to one side of the equation, I have to do to the other. So if I compose the inverse of f of all of this, then I have to compose the inverse of f of this right here. And again, you're just seeing the notation piece in action, where when we go ahead and switch x and y and then solve for y, what happens here is these go away and we get y, and now we see that y truly is the inverse of f of x. So by switching x and y and then solving for y, which is exactly what I did right here, just getting the y by itself, you see that the y is equivalent to the inverse of f of x, and that's what we want. So let's kind of move to the strategies here, and then we'll formalize things up a little bit. It says strategies for finding the inverse of a function, and really the keys here are going to be numbers 1 and 2. So interchange x and y, switch x and y, that's how we're going to create our inverse. Now again, what we want to do is put it in explicit form, so as it says, then what we're going to do is solve for y in terms of x. And number 3 basically states that, well, okay, we've solved for y in terms of x, what does that represent? Well, what we found right here, everybody, and I'll circle that, what we found right here is when we solve for y, that actually is the inverse of f of x. So we really defined that relationship nicely. And then number 4, check with compositions if you need to. Remember the strategy from above, just that verification piece. All right. Well, let's give a few of these a try. And we'll need a graphing calculator for this, so please have that handy. It basically says determine the inverse of f of x equals x cubed plus 1. Determine the domain and range of the function and its inverse. All right, so let's play it all out here. And by the way, it looks like I have 3 examples on this side of the paper. And I would argue it probably goes pretty much, relatively speaking, of course, easy level, medium level, and then hard level. So let's take a look and see what unfolds. So right away, I have f of x equals x cubed plus 1. And another way to say that is y equals x cubed plus 1. That's our function, y in terms of x. Y equals x cubed plus 1. If I want to create the inverse, well, very simply, all I have to do is switch x and y. And that is the inverse. I'm going to actually write that off to the side here. I'm going to come all the way over here. That's the inverse. That is what is called the implicit form. And again, we're not very comfortable working with x in terms of y. Everything for us has been y in terms of x. So once I've created the inverse here, and I'm going to go ahead and, draw that arrow just over, just so you make sure that you see it. Well, basically, all I want to do is algebraically solve for our y, solve for the dependent variable here. And so, without a whole lot of issue, everybody, I think you would all agree that we would want to subtract 1 on both sides. So I'm going to subtract 1 on both sides. And I am going to cube root. So let's cube root both sides. Now, by the way, for a cube root, you do not take a plus or minus, just FYI there. A cube root is called 1 to 1. Every positive number has 1 cube root. Every negative number has 1 cube root. So it's 1 to 1. And so we do not include a plus or minus there. It is just the cube root of x minus 1. And basically what we've now done is change this from implicit form by switching x and y to now explicit form right here. And that's great. And what we saw on the front side is basically this y equals right here is the inverse of our function. It's the inverse of f of x. So we have found the inverse in the form that we wanted. And guys, I'm going to box that up, of course. Okay, so we have the function, we have the inverse. Before we get to domains and ranges, just over here on your paper, just one quick note on this. Remember yesterday's idea, and we kind of built it up just talking about that analogy, wrapping a gift and unwrapping a gift. Well, this is an easy function to work with that idea, because if I sort of asked you the function rules for this, for f of x here, you would tell me cube the input and then add 1. I hope everybody would agree with that. Whatever the input is, you would cube it first and then add 1. So in order to create the inverse, undo those steps. And so I come down here and I look at this and I say, oh, well, you would subtract 1 from the input and then cube root. So again, cube and add 1. Well, here we go, guys. Undo it. Subtract 1 and cube root. And so as a result, you can see that that analogy of unwrapping the gift plays out nicely with being a little more formal here. And again, some of the harder ones you're going to have to be formal on. But it does work, of course. Okay, so let's talk domain and range for this particular piece, and then maybe look at it graphically. So let's talk domain of the function, x cubed plus 1. And I hope you would agree with me that really I can take any number and cube it. There are no restrictions on that at all. So I can take any number and cube it and then add 1. Again, make the connection right away here, everyone. If this is all real numbers, then one of these other 3 you know for sure. And I guess I would argue that it's got to be this one. The domain of the function is the same as the range of the inverse. So even though I haven't even looked at our inverse at all really, but I can tell for sure that its range will be all real numbers. Okay. Well, again, domain we can work with algebraically, so let's go right up here to the domain of the inverse. And in this particular case, cube root. I think I already kind of gave it away a little bit. You can take the cube root of a positive number. You can take the cube root of 0. You can take the cube root of a negative number. There are no restrictions on cube roots, as a matter of fact. And so as a result, that's all real numbers. And what I can then see, and again, we have not been able to do this before unless we had the graphing calculator and analyze the graph, but I could be pretty sure that the range of our function is going to be all real numbers. Okay, let's look at this one graphically. If you get an opportunity here, let's pick up that graphing calculator and let's check it out. So everyone, I'm going to go ahead and turn mine on and go to the y equals, and I'm going to type in x cubed plus 1. Okay. And then the other thing I'm going to do here, I'm going to go into the math menu and find cube root. There it is, my number 4. So cube root, and then how about x minus 1? And don't forget that little line of reflection there. Kind of talked about this yesterday. One part of the function folding over that line and creating the graph of the inverse. So let's go ahead and type in y equals x there. Now I'm going to zoom standard initially and then probably go right back in and hit zoom and then square just to make all the tick marks identical. But I mean, that's pretty good right there. Let's try it one more time. I'm just curious if this is a little better. Yeah, it's fine. Either way I think works. But you can kind of see that piece right there. So everyone take a look. I'm going to try to highlight. Here's the graph of the function. Again, domain and range, all real numbers. Here's the graph of the inverse, kind of like that. And as you can see, look at that perfect reflection over y equals x. If I take this and fold it over this line right here, it should land right on there. I'm going to do just one value thing from yesterday just to make sure we're remembering that. So I'm just going to make up a number here. How about if x is 2? There it is, 2 comma 9. So that's the point on the original function. Where's the corresponding point on the inverse? Well, let's take a peek one more time. And in this case, I'm going to hit 9. And remember, that's still in the function, so I'm going to get down to my inverse, and there it is, guys. So 2 comma 9 was up here, and there's 9 comma 2 down here. Looks great. So all those things that we talked about yesterday work really well. And please, if you don't understand something for this example, just please ask before moving into the next. All right, well, I'm going to get into my next one. And let's see what we have. Determine the inverse of f of x equals 4 over x plus 2. So it looks like I have a rational function here, so that family. And then let's kind of work with the same premise. So I think we can run through this now with a little more strategy and not write every single thing down, but just kind of go through the steps. So right away, this is the easiest part. Create the inverse. And very simply, we create the inverse by switching x and y. So there it is. That is the inverse in its implicit form. Now, of course, the goal is to get it in its proper form, get it in terms of y equals. So that's exactly what I'm going to do. And, well, we have a dilemma here, of course. We do have that y, which we're solving for, is in the denominator of the fraction. So I probably have to remedy that particular situation before moving forward. And I hope you're all right with really taking this and just moving it up here. It's almost like cross-multiplying, but basically you can move that up here, or you're just multiplying both sides by y plus 2, whatever the case may be. But I think that's going to be the case. So I bring that on up. Good, and now what I'm trying to solve for is no longer in the fraction of the denominator of the fraction, excuse me. And then I think, so now I've got to get this by itself. I do have a little multiplication of this x here, and I think I could probably go ahead and divide by that x and bring it on over to the other side. So I've got that piece right there. And then I hope you see it from this vantage point. Let's just bring the 2 on over, and you end up getting something along these lines right here. Again, if any of the algebra is throwing you off, please just stop and ask. But basically, I would bring that y plus 2 up, bring the x on down. You could almost do it simultaneously, to be honest. And then just obviously subtract the 2 from both sides. And there it is. So, not too bad at all here, everybody. I've got the inverse of f of x. Is that right there? I'm going to box that piece up, of course. And remember, if we really wanted to, we could do a composition on this to see if we got it right. I think we did just fine with it, but basically any composition would work. If I take this and replace the input of f, or take this and replace the input of the inverse, again, you should get what you start with. You should get x. All right, well, let's fill in domains and ranges and then take a look at the last one here. So first and foremost, domain of the function. It's the rational family, everybody, and we do have conditions in the rational family. Denominator can't be 0, of course. And so it looks like we are going to have to exclude -2 from the domain, as I can't do 4 divided by -2 plus 2. Simply wouldn't work. Now again, without even graphing here, it looks like we can make a conclusion about the range of the inverse. It looks like with all those function values, with all those outputs, you will never see a y value of -2. Wonderful. Then again, I kind of shoot up to the domain of the inverse. So I'm looking at my inverse. I'm kind of staring at it in good detail. And again, it is a rational function. So the inverse of a rational function is rational. And same premise, everybody. I simply cannot divide by 0. And so x can't be 0 right there, which, again, I think this works out nicely. The range of our function, y can't be 0. And by the way, if you kind of make the connection to some of these things we've seen before, if you looked at this function, I think you would hopefully say that this has a horizontal asymptote of y equals 0. Now, sometimes a graph can cross a horizontal asymptote, but I don't believe that's the case here. And as you can see, 0 is excluded from the range. All right. So again, that was the easy and then the medium problem. And then I think we're ready for the hard one. Same family, by the way. So rational family. And we're going to be a little careful with the steps here because I'm going to have a couple things that I'm going to have to deal with this. So let's give it a try. Right away, instead of y equals 2x plus 1 over x minus 1, we switch. So interchange the roles of x and y. So I should get something like this right here. And if you notice, now we have 2 dilemmas. Dilemma number 1 is what I'm trying to solve for. The y is stuck in the denominator. It's trapped. We've got to fix that. And number 2 is I need to get a y equals at some point. But unfortunately, I have a y down here and a y up here. how am I ever going to get it to a single y equals? Well, let's see what techniques we'll use. Okay, well, I think we can go ahead and do that first step, just like on the last one. And so let's take this y plus 1, and let's multiply it on up here. And so I'm going to get x, y minus 1 equals 2y plus 1. So good first step, no fractions there. Now here's the thing. I don't want to necessarily divide by x, because then I'll have a y here and a y here, and that y will be over an x, and I don't really see that as a good approach. So if you have some intuition here, maybe try a couple things. Pause the video for a moment or two, see if you can get just the y equals just by itself, and I don't know, see if you have the techniques to pull it off. Otherwise, let's go through it together. So I guess in this case, I would argue that unlike the last one, it would probably be beneficial to distribute that left-hand side, because now I can have just 4 individual terms, and I can work with those 4 individual terms. And so if you look, I have xy minus x on the left and a 2y plus 1 on the right. And remember the goal, everybody. The goal is to get a y equals, and then anything else is on the other side. So if I do have to get a y equals, it probably benefits us to put the y terms on the same side of the equation. So what I'm going to do, everybody, is take this 2y, and I'm going to subtract it on over. I'm going to bring it on over to the other side. And while I do that, because again, our goal is to get the y's by itself, I think I'm going to take this x right here, and I'm going to bring that on over to the other side. It doesn't have a y attached to it, so really it's of no use on that side. But I think I'm going to switch the positions of the minus x and the 2y. Okay, now ask yourself, how do I get from 2y terms just down to 1y term? And we definitely have the background to pull this off. Okay, and that technique, of course, to bring this down from xy minus 2y to actually have just a single y written on the left-hand side is to factor. And so everyone, what we're going to do is factor out that y. And when I do, I get exactly what I was looking for, a single y that I can now get by itself. And so I hope everybody does see that last step there. I'm going to go ahead and bring over the x minus 2. And guys, I've got it. So this, in this case, will be the inverse of f of x equals x plus 1 over x minus 2. And I'm going to box that up. And that looks great. So we had our function, and now, of course, we have the inverse to that function. By the way, the 3 that we're doing just on the back side here all do happen to be one-to-one functions. So if you look at the 3 examples on the back, all of those f of x's are one-to-one, which means everything we've solved for is a function independently. All of those inverses are functions by themselves. And again, what we're going to see as we move forward with this is we're going to be working with one particular family of functions called exponentials. It happens to be one-to-one. So when we find its inverse, which we definitely will, it happens to be a function independently, and we're going to do some exploration with that as well. Okay, well, let's wrap this on up here. Let's get domains and ranges taken care of. So I'll start it out here. Again, pause the video if you get a chance and do it yourself. But basically, I would argue that that has to be the case. Domain of the function, anything but 1, which means the range of the inverse, anything but 1. And then if I look at that inverse, again, rational family, do have that dilemma in the denominator there. X can't be equal to 2. And so, of course, y can't be equal to 2. Now, I haven't graphed the last couple, and I'm going to avoid doing that if that's all right with you. But basically, we would see all those characteristics unfold. Anything we've talked about, any of the conclusions that we drew would work for this. Okay, certainly feel free to ask questions if you have them there. Get some practice on this. I like this last one, so really take a look at the ones in the homework and try that out yourself. See if you can do it without looking at the notes. And then if you can't, then please use the notes as a reference. Well, as always, thank you very much for listening, and please let me know if you have any questions.